Okay, so we can convert complex numbers into phasors. We've seen how to do that using polar coordinates. But it turns out we're going to do more than that. We're going to convert our circuits into phasors. We're going to convert our sources into phasor sources. We're going to convert our resistors into phasor resistors. We're going to convert, etc., etc., etc. We're going to take a whole circuit and we're going to turn it into phasors. And it's going to turn out that's going to make our lives actually easier on a problem. Now, we'll start with the resistor, and let me just kind of say here, when I convert a resistor or a capacitor or an inductor, any of those, when I convert them into phasor, the phasor version of them, that is going to be called Z, and the name of that Z is impedance. So it turns out that when I change my resistor, capacitor, inductor into phasors, it's all going to be called the same thing, and that same thing is going to be impedance. And the reason why is, if I take a resistor, then I have Ohm's law, V equal to IR. If I have a capacitor, I have I is C dV dt. If I have an inductor, I have V is L di dt. So these are the relationships between voltage and current in the three elements. But it turns out that when we turn these into phasors, each one of them is going to become V equals I times Z. And that's whether it's a resistor, or whether it's a capacitor, or whether it's an inductor. We're going to get rid of all those derivatives. We're going to get rid of all that stuff there, and it's just going to be V equal to I times Z. And this, by the way, in case you're curious, this is going to be called phasor Ohm's law. Now, what our goal is going to be is we're going to try to want to find what should Z be in order to make this equation true. Well, the thing is, if we compare that to the one for a resistor, well, in order for that to both be the same equation, what you need is you need Z to be equal to R. So it's kind of boring for a resistor. When you get a phasor version of resistor, it is just R. But it's going to be more interesting when we look at the other situations. However, let's look at the summary down here below. When you have a regular circuit, right, you see you have a V of t and an I of t. This is not phasor yet. And then we convert it into a phasor circuit. And the way you're going to know a circuit is phasor is because of these capital bold letters here. And when you have phasor voltage and phasor current, turns out the resistor is still just R. And if you draw the graph between them, then you have this graph that says that the angle of the voltage is equal to the angle of the current, or in other words, the voltage and the current are going to be in the same direction in the phasor diagram here. Or another way of looking at it is when you graph them, they are going to be what's called in phase. And in phase means you have the high points at the same point, the zeros at the same point, you have the low point, same point, and so on. That means they're going to be in phase or always going together. And so this is the most basic element we can deal with, and it works out quite nicely.